I got an email from Mike Jarowitz. He's not able to join us today because, all right.
Hi there, everyone. Welcome to the National Weather Association's webinar Wednesday for November. I'm Joe Murgo. I'm going to be your host for today's webinar. I'm a meteorologist at the CBS affiliate in Altoona and State College, and been involved in broadcast meteorology for a couple of decades now. I guess I'm getting old, and also I've done some operational forecasting at AccuWeather and do some consulting on the side. A few logistics before we get started. All attendees will be kept on mute for the entirety of the talk. We encourage you to ask questions or make comment to our speaker, but do so using the questions GUI or raise your hand feature on the GoToWebinar, or ask a question on Twitter using the hashtag NWAWebWed. I'll read the questions and comments at the end of the presentation. You can follow along the presentation on Twitter using the same hashtag, or follow the NWA account at NWAS. Lastly, this webinar is being recorded for viewing later on. This month's webinar is about using the multi-sensor advected layer precipitable water a product in operational forecast environment. I'm real interested in this because we had some very bad flooding situations here in central Pennsylvania. So I'm very pleased to announce our speaker today, which is Christopher Gitro. Sorry, Chris. He's a lead forecaster at the National Weather Service in Pleasant Hill, Missouri. Take it over, Chris.
Oh, good afternoon. Good morning, everyone. Thanks for the nice introduction. And this is a product that I've become very familiar with over the past couple of years. And fortunately, I've been able to work with some great people on analyzing this product and determining how well it would be for operations for the meteorological community. So we just published a paper in the NWA Journal of Operational Meteorology, and I was asked to give a presentation this afternoon on the possible uses and some of the benefits that this type of product provides for forecasters as they make forecasts on a daily basis. So we'll go ahead and get started here. Just a brief overview of what we're going to be talking about today. We're going to briefly take a look at some of the flood fatality trends over the recent couple of years, and with some examples of some high impact events. We'll also briefly talk about the history of the multi-sensor water vapor products and how they've been incorporated into operations in the meteorological community. We'll talk about briefly some of the motivation behind the advected layer precipitable water product, which we'll be discussing in detail today. Also some of the advantages as well as examples and some of the community benefits that this type of product can provide all members of the operational forecast community as we go forward here into the future. So some of the national trends and recent examples of significant flash flood fatality events across the United States. So the 30-year average for flood deaths across the United States averages roughly around 85. I just looked these numbers up a couple of weeks ago just to verify. However, the 10-year average has increased to about 93 annual flood deaths. And just last year alone, we had 116 deaths across the United States attributed to floods. So the trend definitely seems to be going up across the United States with respect to flood-related fatalities. So a couple of the big events that many of us are probably familiar with in the past couple of years, going back to June of 2010, the Albert Pike flash flood tragedy in southwestern Arkansas. Significant flooding impacted a campground there and carried many away till their deaths during the overnight hours. Back in 2013, May of 2013, in the Oklahoma City tornado and flash flood situation resulted in 20 fatalities. Also, the Colorado Plateau Hilldale, Utah event in September of 2015 resulted in 20 flash flood fatalities. And then in South Carolina, many of us are intimately familiar with this event back in October of 2015. Significant moisture advection from the Atlantic over portions of the Carolinas resulted in 19 flood fatalities. And the West Virginia flood is one of the cases that we'll be discussing today in June of 2016. resulted in 26 flood fatalities. And as one of our panelists here can attest to, Sheldon Cusselson lives not too far from the Ellicott City, Maryland area, and they've had 2 1,000-year events in the past 3 years, which resulted in significant flooding across portions of Ellicott City and 3 combined fatalities. So now we'll talk briefly a little bit about the history and the creation of multi-sensor satellite products. But first, we need to talk a little bit about some of the acronyms that we're going to be using through the course of this presentation. So TPW, or total precipitable water, pretty much is the condensed depth of water from the surface all the way up to space. And many times in the meteorological community, it'll be referred to precipitable water, PWAT. When we talk about layered precipitable water, we're going to be talking about the condensed depth of water vapor in one specified atmospheric layer. And then to add on to that a little bit, we'll be talking about the advected layered precipitable water product, which is ALPW, but just in the advected component. So layered precipitable water really can be defined as the integral of the mixing ratio through a pressure layer divided by gravity. So ALPW is really proportional to the mean layer mixing ratio through an atmospheric layer. So looking at a clock diagram at some of the satellites that are used to create layered precipitable water data, there's currently 7 satellites that go into the creation of layered precipitable water, and NOAA 20 will soon be added to this constellation. And just last night, the METOPC satellite that was launched by our European brethren, and that will eventually be incorporated as well. But water profile retrievals are created through the MIRS sensor aboard several polar orbiting spacecraft, and that those data retrievals are used for the production of blended total precipitable water as well as layered precipitable water products. And historically, as a result of different time sampling through the, as satellites are working over the Earth, that's led to making animations for forecasters rather challenging to interpret at times. And we're going to show how, by looking at the advected layer precipitable water product, many of those sampling issues are largely removed. So looking, continuing on with the history of this type of data, back in 2009, CIRA's blended total precipitable water in percent of normal products became operational in the operational forecast environment and made available to National Weather Service forecast offices and AWIPS. And the total precipitable water product displays the total integrated moisture from the Earth's surface all the way up to space. And one thing that we noticed and found, as we started to look at this data in the operational environment was it's very sensitive to low-level moisture contributions and fails many times to track and detect contributions from further aloft in the atmosphere. And it's still a very highly versatile product, leading up to periods of heavy precipitation over the United States and even over the world, because this is a product that's produced over the entire world. However, one of the significant issues associated with this product is really that it fails to detect moisture contributions from middle and upper portions of the atmosphere, and it's very sensitive to the low-level moisture contributions. So over here on the far left, I got a loop there of the total precipitable water product, and over on the right, there's a static image there of the percent of normal product that is available to us in AWIPS and the Weather Service, and also available online from NESDIS for anybody that's not in the Weather Service, that they'd be able to view in real time. So in 2013, CIRA introduced the non-advected layered precipitable water product. This was, we started looking at this operationally in the Weather Service via the internet source that was provided by CIRA. This product is at a 16-kilometer resolution, and it's available in 3-hour increments. And the water vapor retrievals from the MIRS instrument aboard the polar satellites is available in cloudy regions. However, data and areas of precipitation ultimately get flagged, and we'll show examples of that. However, we strongly feel that this is a significant improvement over the traditional water vapor imagery because we're actually able to see through clouds, whereas traditional water vapor imagery doesn't offer that capability. We currently have 4 predetermined layers, the surface to 850, 850 to 700, 7 to 5, and 5 to 3. And this product is ultimately created through stitching together multiple different satellite swaths, and then using GFS winds, or excuse me, this product is created just through stitching several different observations together, and then forecasters are able to look at that animation in real time. So here's an example from August 27, 2016. This was a significant flash flood event for the Kansas City metro area. And you could actually see, how we have precipitable water values broken up into the 4 predetermined layers of the atmosphere, and we're actually able to see contributions at those individual layers as they move forward in time and potentially result in heavy precipitation over a given location. So this is, like I said before, this is a rather significant improvement over the blended total precipitable water product because we're actually able to see contributions at multiple layers, whereas the total precipitable water product is really seeing the strongest contributions from the lower portions of the atmosphere, and it's not partitioned into individual layers like the layered precipitable water product is. However, there are some issues with this product, as we stated, or as I stated a little while ago, about the stitching together of multiple polar satellite passes. You could actually see those swath lines from the individual polar satellites as they work over a particular area, and ultimately this has kind of made it difficult for operational forecasters in the operational environment to use this data. Because of the data discontinuities and the satellite swath lines, etc. So, but still a very versatile product, and we've been able to find over the past couple of years just how much improvement in the situational awareness that is provided to forecasters by being able to track moisture contributions at multiple different layers of the atmosphere in advance of a significant precipitation event. So in 2013, NASA Sport did a study with several forecast offices along the West Coast, as well as Puerto Rico and Alaska, and they wanted to gauge how well forecasters thought this type of data impacted operations. And overall, the results were very favorable. Very high with regards to how forecasters felt on how much improvements or how significant the addition of layered precipitable water in the forecast environment led to situational awareness and how much it improved the overall forecast process for them as they were able to track moisture contributions from multiple different layers over towards a specific area. So just looking at the middle graph there, how well would you rate the value of having the layered precipitable water product compared to the standard total precipitable water product that we discussed earlier, and the response from the forecasters was very large in that it made a significant improvement over the total precipitable water product. So overall, as this continues to gain traction in the operational environment, the results and the feedback from forecasters has been very positive on the type of the increased situational awareness that this product offers to forecasters in the operational environment. So going back to this slide here, where we looked at the multiple different satellites that are used to composite the layered precipitable water product, we briefly spoke about how the periods of high sampling and no sampling at times can make the animations difficult for forecasters to interpret at times because of the satellite swath lines and other data discontinuities. But when we look at the advected layered precipitable water product, a lot of those data discontinuities are smoothed out, and as a result of that, it becomes much more favorable and user-friendly for forecasters to use operationally, as many of those data discontinuities and satellite swath lines are largely removed. And that's going to be the focus for the remaining portions of this presentation, on how well the advected layered precipitable water product improves upon the original layered precipitable water product. And we'll be able to show some examples of that as we move forward here. So in 2016, CIRA introduced the advected layered precipitable water product to the operational environment. Many of the parameters are the same as compared to the original layered precipitable water product. However, with this product, the water vapor features are advected forward in time with GFS winds to a common time. So by doing that, we're actually able to remove many of the CIRA is actually able to remove many of those data discontinuities that we were speaking about previously. So it's actually using the GFS winds to move water vapor retrievals forward in time, which helps smooth out the data and makes it much more digestible, if you will, for forecasters to interpret in the operational environment. So here's an example. We previously looked at the Kansas City flash flood emergency event from August of 2016. Here is the advected layered precipitable water example leading up to the period of heavy rainfall over the greater Kansas City area on this day. And overall, it just looks much more better with respect to interpreting the data as a result of many of those satellite lines, there's swath lines being removed. And notice on all four panels, the areas of black, that's where the mirrors profiles that are retrieved from the satellite are being flagged as a result of areas of ongoing precipitation. So here's now if you look at the non-advected next to the advected, you can see, just an overall, much of that pixelation that you were noticing with the 16-kilometer pixels in the non-advected component, much of that is actually removed with the advective component, and it's just overall much more appealing, visually appealing to an operational forecaster as he or she is making a forecast and trying to determine, different sources for moisture in advance of a significant precipitation event. So we have this available to NWS forecasters in AWIPS, and if there's any forecast offices that are not currently receiving this data, simply just contact Dan Bicus at CIRA, and he'll give you instructions on how to start ingesting this data, and we'll provide his contact information at the conclusion of this presentation. For any of those who are not in the National Weather Service and are interested in looking at this data in real time, the link is provided at the bottom of the screen here that can be accessed anytime and used operationally for those who are not in the National Weather Service purview. So we decided to go ahead and do a little study, and one of the main hypotheses of the study were that the advected layered precipitable water product is actually able to capture distinct plumes of moisture at predetermined layers and are critically important for analyzing the possibility for heavy rainfall. And also, once we identified those moisture plumes, our hypothesis was that moisture associated with the plumes would be sampled by radiosonde observations, which could ultimately help infer and prove that we're going to have a higher level of precipitation, the higher likelihood of precipitation. And through that, we'd be able to look at forecast soundings and see how warm cloud layer depths were going to be increasing. Historically, many of us in the Weather Service have been trained. Warm rain processes are pretty much paramount for significant precipitation production and highly efficient precipitation production, as rain is produced through the collision and coalescence process. And typically we look for warm cloud layer depths of 3 to 4 kilometers or more, and that actually helps support tropical rainfall rates as rain is generated through the collision and coalescence process. And that's something that we operationally in the forecast community are looking at very significant or constantly as we try to determine whether or not a specific weather system of interest is going to be capable of producing rainfall rates that could result in significant flash flooding. But by looking at forecast soundings, we're looking specifically for deep warm cloud layer depths that will actually support that warm rain process of collision and coalescence of precipitation production. So before we do that though, it's important to look at why mid and upper level moisture transport is important for heavy rainfall. So going back and looking at some of the previous literature on using satellites for the detection of environments that are supportive for heavy rainfall, back in 1995 a paper was published where they identified water vapor plumes that extended all the way up from the tropics, and that was identified by the original GOES 6.7 micron imagery, just standard water vapor imagery. And through the course of their study, they were able to show that water vapor plumes at times can become aligned with low and mid-level theta E ridges, which are regions of typically high instability and abundant moisture availability. And through a 3-year period, they identified 129 heavy rainfall events, and 83% of them had water vapor plumes, and 83% of those had original or origins in the tropics. And you can see here on the bottom left here, we're really trying to identify atmospheric rivers as significant moisture advects poleward from the tropics, and that's where the ALPW data actually helps us out. So also in 2000, Schofield et al. Came out with a paper where they were actually able to show how these water vapor plumes can be highly efficient rainfall producers as a result of cloud seeding from above and the ultimate limiting of dry air entrainment. And many of us have probably seen the Doswell et al. 1995 flash flood ingredients paper, and they specifically discussed at length about how the lack of dry air entrainment is a very important contributor for improved precipitation efficiency. So the ALPW data helps us really identify these types of environments as we see moisture plumes from the Pacific or from the tropics move poleward into the continental United States and elsewhere that could ultimately lead to significant periods of precipitation. So let's take a look at a couple of examples here. First, we'll take a look at the early September 2014 Northern Missouri event, and then we'll cap it off with looking at the infamous West Virginia case, June of 2016. So looking at the Northern Missouri event, here's a 4-panel of the advected layered precipitable water imagery approximately 24 hours prior to the period of heavy rainfall and the issuance of the first flash flood warning. On the maps here, you'll see the yellow asterisks. That will represent the sounding location, in this case, Kansas, whereas the white star represents the area of heavy rainfall and flash flooding. The big thing of interest on this panel is if you look off the Baja California coast, you'll see the remnant circulation of Hurricane Norbert, and that's going to be shown to be a pretty significant contributor to the amount of the heavy rainfall likelihood over the central U.S. As this event continued to evolve in time. So, looking at the total precipitable water imagery, this was roughly around the same time. You could ultimately see the remnant Hurricane Norbert circulation there off the Baja California coast, high levels of precipitable water being sampled by the polar satellites. But notice over like central Colorado, Wyoming, and the northern portions of New Mexico there, that there's a relative min as sampled by the total precipitable water product, the blended total precipitable water product. And as we stated previously in this presentation, that's one of the limitations of the total precipitable water product is that it's receiving its significant moisture contributions from low level portions of the atmosphere as opposed to mid and upper level portions. So The 0Z sounding from Topeka, Kansas on 9 September. And right now we're looking at warm cloud layer depths of roughly 4.1 kilometers. And like I said previously, we're really trying to isolate environments that have warm cloud layer depths of 3 to 4 kilometers. So even 24 hours prior to the event, we had a pretty moist atmosphere in place for this case. So looking at a 36-hour loop of the advected layer precipitable water product ending at 3Z on the 10 September 2014, you can see specifically on the 7 to 500 panel and the 5 to 300 millibar panel that we're seeing significant moisture contributions in the middle and upper level portions of the atmosphere. And I even tried to annotate this by white arrows, and you can see how moisture associated with Hurricane Norbert, or the remnant circulation of Hurricane Norbert, is actually working over the Intermountain West, Central Rockies, into the Central Plains and Lower Missouri Valley. And as we discussed on the previous couple of slides, that just simply was not being sampled by the blended total precipitable water product, as that product, as we discussed at length, is most sensitive to low-level moisture contributions. So this case really shows, this animation really shows how, the mid and upper level moisture contributions that were not sampled by the total precipitable water product did in fact have a role in the heavy rainfall likelihood downstream over the Lower Missouri Valley for this case. So as that moisture continued to move into the area, this case really was able to show how the mid and upper level moisture contributions as sampled by the advected layer precipitable water product gradually increased with time. And you can see how with the 30-hour ALPW trace, that just gradually increased throughout the period leading up to the period of heavy rainfall. So if you follow the blue and the green lines, you can see just how the values of precipitable water as sampled by the ALPW product just continue to increase with time. And you can see there in the upper right, we had some areas near Kirksville, Missouri, that got close to 10 inches of rain through the course of this event. And as we discussed a couple of slides ago, the atmosphere was already pretty moist in this case, but the warm cloud layer depth ultimately did increase to 4.5 kilometers, and that's rather impressive and supportive for the warm cloud layer processes to dominate for precipitation production. So this table illustrates how moisture sources from distant regions can really influence the potential for heavy rainfall. In this case, the Hurricane Norbert, the remnant Hurricane Norbert circulation as detected and tracked by the ALPW data, and the heavy rainfall ultimately in the improved precipitation efficiency as a result of mid and upper level moisture contributions as detected by the ALPW imagery, which combined with the warm cloud layer depths increases from the low level moisture injection from the Gulf of Mexico really resulted in a significant rainfall event for the Lower Missouri. So what we really think is going on is the warm cloud layer depths have a substantial component from the low level moisture contributions, but the upper level moisture contributions as detected on the ALPW imagery really ultimately help lead to the increased precipitation efficiency through cloud seeding from above and the limitation of dry air entrainment. So you have two processes actually working together there and resulting in the increased likelihood for significant heavy rainfall. So let's take a look briefly at the 2016 West Virginia case, a pretty significant case for the Central Appalachians. 24 hours prior to the heavy rainfall event, you can actually see over West Virginia that even on the low-level panels, the surface to 850 and the 850 to 700, that your precipitable water values aren't ultimately that great, and that's because a front had actually moved through the area, and that is actually sampled well, especially on the 850 to 700 panel there, that the higher precipitable water values, if you will, have been shunted to the south as a result of that frontal passage. In this case, we'll be looking at the Wilmington, Ohio sounding location in southwestern Ohio, and then the star there is going to be, again, the area of heavy rainfall that occurred across West Virginia in the next 24 to 36 hour period. So looking at the 12Z sounding from Wilmington, Ohio, we see a warm cloud layer depth in this case of roughly 2.1 kilometers. So that's right now at this point is under that 3 to 4 kilometer threshold that we really try to look at with respect to favorable conditions for warm rain processes that dominate for precipitation production. And the total precipitable water product, shows some higher values there across the Tennessee Valley, down into the Carolinas. This is a 36-hour loop, but most specifically, I draw everybody's attention to the Intermountain West once again, the Central and Southern Rockies. You could see just a relative min in the precipitable water values that are actually being sampled, and as we'll show here in the next couple of slides, that again is attributed to the fact that that this product is most sensitive to the low-level moisture contributions. So here is a 36-hour loop of the advected layer precipitable water product, ending at the time of when the first flash flood warnings were issued. And most specifically, I draw everybody's attention to the 7 to 500 and the 5 to 300 millibar panels down at the bottom here. And you can see, especially on the 5 to 300 millibar panel, it shows up very, very nicely how moisture from the the East Tropical Pacific was actually converging over the Central Rockies and actually working downstream over the Missouri Valley into the Tennessee and Central Appalachians area as this event continued to evolve. And if you go back, if we think about what we just saw on the previous slide, those moisture contributions over the Intermountain West, over the Central Rockies, they were not sampled at all on the blended total precipitable water product. So this is a distinct advantage of the advected layer precipitable water product, is we're actually able to see better contributions in the middle and upper level portions of the atmosphere. The moisture is actually partitioned out to the creation process by looking at the mirrors profiles, and you could just see how impressive this is, in my opinion, of how significant moisture contributions from the Eastern Pacific actually work downstream and ultimately help result in a fairly efficient rainfall environment over the Central Appalachians. In contrast to the advected layer precipitable water product, this is the traditional layered precipitable water product, the first product that was ultimately released by CIRA. Again, you could see the contributions from the East Tropical Pacific working east over the Intermountain West and Central Rockies, and eventually down into the Central Appalachians. But however, you can notice the difference. There's greater pixelation, and there's areas of data discontinuities and swath lines, and that's a result of this being the non-advected ALPW component, where the GFS winds are not being used to advect water vapor retrievals forward in time. So, water vapor profiles forward in time. And you could just, compare and contrast between what we just saw in the previous slide. This is just so much more visually appealing, in my opinion, to a forecaster, and more easily digestible, if you will. The ALPW data is compared to the traditional layered precipitable water product. So in this case, rather significant moisture contributions, I thought, especially in the 7 to 500 millibar layer. If you look at a 27-hour ALPW trace, you can see the blue line there on the bottom right increased rather substantially. The warm cloud layer depth at the Wilmington, Ohio sounding location ultimately increased to 3.9 kilometers. So at this point, we're above that 3 kilometer threshold that we look at for precipitation production from warm rain processes. So this is just ultimately becoming a much more efficient rainfall producing environment as those warm cloud layer depths continue to increase. So this case really illustrates pretty clearly, in my opinion, how moisture sources from over 2,000 kilometers away can ultimately impact an area flash flooding. In this case, we saw those Eastern Pacific moisture plumes converging over the Central Rockies and working downstream into the Central Appalachians along the northern periphery of an upper level ridge that was in place, and ultimately help result in a fairly efficient rainfall environment over the Central Rockies. And also, the ALPW data, in my opinion, is just decidedly better at showing those upper level moisture contributions as compared to the original total precipitable water imagery that was released back in 2009. So as we start to wrap things up here, we'll take a look briefly at how some of the national centers are using this data in real time. So here's an example from the Weather Prediction Center from back in August of 2018 here. Here's an example of one of their mesoscale precipitation discussions. Here they were focused on heavy rainfall potential across southeastern Arizona and southwestern New Mexico. And you could see how they're actually mentioning the CIRA layered precipitable water products in there and discussions as they're, sending these out to forecast offices to increase their knowledge of an environment that's becoming more supportive for heavy rainfall production. And this product's being used operationally at the Weather Prediction Center. And the next example illustrates that as well. Here's another mesoscale precipitation discussion from back in February of 2018. And again, they specifically talk about how moisture plumes as detected on the CIRA layered precipitable water products really reveal good fetch of tropical moisture working north over the over Mexico into Texas, etc., and increasing the likelihood for significant heavy rainfall. Mike Jarowitz, a co-author of mine and a really close friend, talked about, he sent out an example of how this product was used for a significant heavy snow event in the Northeast. This was an example of significant lake effect snow with moisture wrapping around an upper level low and working southeast over Lake Ontario. And I talked to Mike briefly last week about this event, and the moisture contributions that were shown on the layered precipitable water product, greatly increased his situational awareness that a long fetch of moisture was available as detected on the ALPW data that was going to result in a continued environment that's supportive for significant snow generation. And this was the event that set a 24-hour snowfall record for the Binghamton, New York area, 24-hour record. And Mike was able to see this on ALPW data, which greatly increased his situational awareness that this was going to be a bona fide significant winter weather event. And sure enough, it was, as the 24-hour snowfall record was broken in Binghamton, New York on this day. Also, the National Hurricane Center continues to use this product operationally as well. In August of 2018, the ALPW product was mentioned 72 times in their tropical weather discussions, and it was greatly, it just appears to be a greatly utilized product at the National Hurricane Center as well. So another example of one of our national centers who are using this data operationally and including in their forecast discussions. So another example there. So the CIRA people, Dan Bicus, etc., they've been able to help share this data with forecast offices across the Weather Service. Currently, there's roughly 20 offices that are receiving this data in the AWIPS-2 configuration, as well as the Weather Prediction Center and National Hurricane Center. And if there's any forecast offices that are out there that are interested in utilizing this data in AWIPS or getting this access to this data, simply contact Dan Bicus, and his email's at the end of this presentation, and he'll be able to provide instructions on how to get this data in AWIPS for you. Just an example here from the Tucson Weather Office talking about how the ALPW product has been very useful and very helpful for them in the operational forecast environment. And Dan Bicus and Sheldon and Ed Zoke from CIRA, they were nice enough to create a training session as well on the advected layer precipitable water product. And for those that might be interested, the link to that presentation is included towards the top portion of this slide, and also included at the end of the presentation as well. So this product has also gained quite a bit of attention on social media, and we have Sheldon Cusselson to thank for that. Sheldon's a long-term, a now retired forecaster from NESDIS heavy precipitation branch, and he's now working with CIRA to help develop training and stuff like that for utilizing the ALPW data in the operational setting. And Sheldon's been very helpful in getting the word out, if you will, on utilizing this type of data in the operational forecast environment. So over here on the far left is an example of one of Sheldon's analyses that were where he compared moisture contributions between Michael, Harvey, and Florence, and that was actually picked up by the Alabama Weather Blog back in October of 2018. Also, he did a nice comparison, or a nice analysis once again, of the Ellicott City, Maryland event back in 2016, as well as the Kansas City flash flood emergency, one of our first flash flood emergency here in the Kansas City metro area back in 2016 as well. Couple posts there on during NWA back in 2016. And just another example of the comparison between Harvey and Florence back here in September of 2018, where Sheldon was nice enough to share some of his analysis for many to see. So if anybody's interested, I highly encourage following Sheldon on Twitter, and he can be found at Weatherman27. And I follow him quite a bit, and we talk back and forth about some of the things that we're seeing on the layered precipitable water products. So it's just a continuous learning environment between all of us, trying to learn how to best utilize this type of data operationally. And special thanks to Sheldon for continuing his work on advertising this, the benefits of this product to the operational forecast community. So probably the best part, in my opinion, on doing this study with CIRA is the fact that we're merging NOAA as well as the research community, and we're gauging everybody's expertise, and we're ultimately creating products that are new products for the operational forecast community that benefit everybody, that everybody can be able to use. And also we're creating research efforts for the future as well, and we're currently looking at how this type of data could be used for severe weather environments, and we're always looking for new ways how this type of data can be used operationally. And the relationships that we've been able to forge have been fantastic, and will hopefully continue for many years to come as additional satellite data sets become available and to the operational forecast community as well. So in conclusion, the ALPW data greatly improves the overall quality of the precipitable water fields as detected by the polar satellites. We've shown that the ALPW is very sensitive to tracking long-fetched moisture plumes over considerable distances, especially the upper levels, the 7 to 500 and 5 to 300 millibar layers. The ALPW overall gives a very clear picture to forecasters operationally of the multi-layer moisture distribution in the atmosphere. And like I said before, if anybody's interested in any weather service folks or anybody in the operational community in general who are interested in this data, the links provided there, and just contact Dan Bicus for instructions on how to get this into AWIPS. And we're continuing to explore additional forecast applications as well. We're currently looking at how this data can be used to help track elevated mixed layers as they move away from their as they move away from their source regions for severe weather environments. And we're also looking at winter weather applications as well, trying to parse precipitable water information into the dendritic snow growth region for heavy snowfall production as well. So many different projects, many different things in motion here, and it's all been a great benefit, we think, to the operational community, and we look forward to sharing our results with everybody here in the future. So if anybody's interested in looking at the training page that CIRA created, or the training session that CIRA created, just follow the link there at the bottom of the screen, and I'll be happy to entertain any questions. And once again, the visit training's there, as well as the website. For those who are not in the Weather Service, they can look at that data online in real time. So thank you very much, and I'll be happy to entertain any questions.
Well, thank you very much, Chris, for your informative talk. It was a great discussion, and made me start to think about looking up higher in the atmosphere for some heavier precipitation events. And I'm also looking forward to taking a look at this in the winter, and even looking, so you're seeing, I'm going to start off with one question before we go to other ones. So are you seeing maybe that some of the coastal storms that we get here along the East Coast, we should be looking up at the higher levels to see if there's specific moisture moving all the way across?
Absolutely. I mean, I think having a good understanding of the moisture distribution in the atmosphere is paramount for successful forecasting operations. I've worked so many events where we've actually gotten dry slotted, and we've gotten much less snow than what we actually thought we were going to get, and I think utilizing this product operationally for wintertime forecasting will be very beneficial to ensure that we have knowledge on the vertical structure of the moisture distribution in the atmosphere, and providing knowledge or situational awareness that dry layers might be working into a particular area, which could ultimately limit the amount of snowfall production that could be expected over a given area. So I think, yeah, absolutely, looking further aloft in the atmosphere is going to be greatly beneficial for winter weather forecasting.
Yeah, and you actually brought up something that I didn't think of, which is really important, is sometimes not just highlighting the areas that get the more snowfall, but the areas where maybe it's not going to be as bad because of the implications on people across the nation.
Yep, most certainly.
Does anyone else have a question that they want to pose? Please, real quickly, put it in the GUI or send it out on Twitter. Hannah just made a interesting thing, and it is sad that we are seeing so many more flood-related fatalities on the rise. Now, some of that has to do with population growth, but Chris, I'll ask you, because I've been doing some studying on this too. Are you finding that there is more moisture in the atmosphere overall in the past 5-10 years?
I think that's kind of a hard question to answer. I mean, this data we've only had available to us in the past couple of years, operationally speaking. I'm not sure, to be honest. I mean, I think that's a great question. I don't know if I'm in a position to really try to answer that. I mean, if you go back and look at flash flood fatalities, and I always go back and look at the 1970, I think it was 1972, the Rapid City, South Dakota event that led to close to 300 fatalities. Our nation is by no means it's by no means new that we're experiencing such significant fatalities, but the 30-year average, if you will, recently the 10-year average is really showing that we're continuing to increase the number of fatalities that are occurring nationally. And whether it's attributed to poor decision making or people not receiving warnings, that's more of a social science type of question to answer. But I think overall, by incorporating data from the layer of precipitable water, we're going to be greatly increasing the situational awareness that forecasters have for detecting environments that could become supportive for significant rainfall production.
Yeah, and we can have the best tools in the world, but unless we get the message out and people
Absolutely.
listen to the message, that's important too.
No doubt.
All right, last call for any questions, and I know you can always contact. You see everyone's Twitter handle there, and you have also emails. So please, if you feel as you're watching this down the road on the recorded webinar, shoot them an email. And yeah, all right. Well, thank you very much, Chris. That's all we have for now. Next month's webinar, again, will be hosted by our social media committee, so stay tuned for details. Thanks again, and we'll see you all next month.
Okay.